So hopefully you've all had a chance to see your progress reports. I put them all in the chat yesterday. So if you haven't done that yet, just click on chat and then they're there. And then show your parents or guardians or whatever. And then that way, yeah, we're good. For today, so I want to go over some questions. I don't know how much we're going to get done. Well, we're gonna get one lesson done for sure, but I don't know how much more than that I want to get done today. So we'll just focus on the one lesson and see what happens after that. So before that, are there any questions on stuff we've done so far? Gravity, circular.
I have a question for worksheet 2.
Okay.
Can you go over number 3?
Okay.
Worksheet 5.2. No, question
3?
Yeah.
Yes. Okay, so that one. Okay, so a student has a weight of 655 newtons. While riding a roller coaster, they seem to weigh 1.96 times 10 to the 3, so that's a lot heavier, at the bottom of a dip that has a radius of 18 meters. What is the speed of the roller coaster? So if you think of a roller coaster at the bottom of a dip, it's going in a circular motion that is like this. So if you complete the circle, it's going this way. So that means that our centripetal force is whatever force is going up at that point. So if you were to draw the forces acting on the roller coaster at that point, you have Fn going up and Fg going down. Okay, and then the Fc would be the net force acting on that. So it would be Fn minus Fg. Okay, now in this case, the student normally has a weight of 655 newtons, so that's Fg. And when they seem to weigh, that's Fn. Okay, apparent weight is Fn. And then we have the radius as well, and we want to find the speed of the roller coaster. So in terms of everything we have, well, let's find Fc first. So Fc is going to be, this is going to be 1,960 newtons. That's our apparent weight, minus the actual weight, 655 newtons. So 1960 minus 655. And so we get Fc equals 1305. Okay, that's the newtons. And then we have to go mv squared over r equals 1305. Okay, because Fc is mv squared over r. To get m is a little bit tricky, I guess. Fg equals mg. And so Fg is 655 equals m times 9.8. Okay, so 655 divided by 9.8 is 66.8. So then we get 66.8 times v squared over 18 equals 1305. What does it say? Can you go over 9 and 10 for 5.3? Yes. And then so we're going to take that 1305, multiply it by 18, divide by 66.8, and then square root, and we get 18.7. 18.7 meters per second. Okay, does that make sense?
Yep. Thank you.
Okay. So yeah, it's the seam to weigh part is Fn. It's the normal force.
Could you go over question 4 and 8 from the same worksheet?
Sure. Okay, number 4 and 8. Okay, string required, tied to the string and whirled in a vertical circle. What is the maximum speed? Okay, so again, if something's whirled in a vertical circle, then the tension is maximized at the bottom of the arc. And so the Fc at the bottom, you have tension going up and you have Fg going down. So Fc will be T minus Fg. So then it requires 186 newtons of force to break. So let's set that as our maximum. So we have mv squared over r equals our maximum 186 minus mg. Okay, and then you can just solve for v. So 1.5 v squared over 1.9 equals 186 minus 1.5 times 9.8. 186 minus 1.5 times 9.8 equals 171.3 times 1.9 divided by 1.5, and then square root equals 14.7. Okay, but all you have to do here is understand that the tension is maximized at the bottom of the arc, and that's why we set it up at the bottom. Number 8, airplane is traveling at a speed of 150 meters per second, makes a complete horizontal turn in 2 minutes. What is the banking angle? Okay, so let's assume that the plane is going like that, and then it's going around. So then we're going to have, like, we'll call this F lift or FL, and then FG. And so FL, the lift plus the FG will equal the FC. And the banking angle will be this angle right here. It's an interesting question. And so we're going to go tan theta equals FC over FG. Tan theta equals M times 4, mv squared over R over mg. And so tan theta will equal v squared over rg. And so 100, well, not do that. Tan theta equals 115 squared over, oh, we don't have r. Crap. We have to find r first. Okay, so to find r, we're going to go v equals 2 pi r over t. So 115 equals 2 times pi times r over 120. Right, that makes sense. Okay, so 115 times 120 divided by 2 pi is, so r is 2,196 meters. Okay, so then we're going to go 115 squared over 2,196 times 9.8. 115 squared divided by 2,196 times 9.8 equals, and then second tan that, inverse tan, and you get theta is 31.6 degrees. Okay, so there's a few things there. There's the drawing of the airplane. Like, obviously, if an airplane is flying like this, it's flying straight. But if an airplane flies like this, it's going to turn that way. So that's what we're doing. And it's just like our banked curve with a car, right? If the car is going like this, we have Fn going that way, we have Fg going that way. If you add them together, you get Fc. Okay, so pretend this is the airplane. The only difference is that you have the lift from the wings. And then if you add them together, you get Fc. Okay, and the angle, remember that the bank angle here, whatever angle it's banking at, is going to be formed between the two forces, the two forces you're adding, so FL and FG, so that's why this angle's here. And then tan theta that, and then you just have to cancel out the masses and choose the right formula. Does that make sense?
So is the airplane going in a vertical circle, not a horizontal?
No, it's a complete horizontal circle.
Okay.
Right, so like if you see an airplane, like we're seeing the airplane from behind right now, it's going away from us. It's going to go around, and then it's going to be coming back towards you, and then it's going to complete the circle like this. So it's a horizontal circle.
Okay, yeah, got it.
Like it's maintaining its altitude. It's not going up or down.
Okay.
It's a good question. Okay. Any other questions before we get to 9 and 10 on 5.3? Okay, number 9. 3 objects, A, B, and C, are placed 0.5 meters apart along a straight line. On A and B have mass 10, 15. What is the net gravitational force on B due to A and C? Okay, so whenever we have questions like this, because we'll have questions like this with electrostatics as well, it's so you have to ask yourself what's happening to B based off of A and C. So if you were to say, because it's asking what is the net gravitational force on B due to A and C, B is the thing that is moving and A and C are just fixed. Okay, so because A is a mass and B is a mass, there's a force of gravity going this way. Okay, and that's because A is attracting B. And there's also a force of gravity going this way because C is attracting B. Okay, now there's also a force of gravity going this way because B is attracting A and B is also attracting C. Okay, but we're only interested in what forces are acting on B. Okay, so what we have here is like, we'll call this FGA and FGC. The net force acting on B is going to be FGC minus FGA. Okay, and then all we have to do is plug those in. So F net is going to be FGC, so that's going to be, and I'll try to do this. I'll do it this way. So G MB MC over, and then I'll just call this R squared, and remember the R is 0.5 for both, and then minus GMB MA over R squared. And the reason I'm writing it out like this is because I know that I can factor things out. Okay, GMB over R squared is the same for both, and then all I have is MC minus MA. Okay, so notice how GMB over R squared is the same for both. So if you factor those out, you're left with MC minus MA. So if you multiply this back in, distribute, and you get the exact same thing. So then the net force will be 6.67 times 10 to the negative 11 times 10, because that's MB, over 0.5 squared. And then MC 15 minus MA 10, 6.67 times 10 to the negative 11 times 10 times 5 divided by 0.5 squared is 1.33 times 10 to the negative 8 newtons. So got the right answer. Okay, you don't have to do it that way. You can actually do, like, you can solve this, but because we're using such big numbers, if you can factor things out and only do them once, it's easier to write, I guess. Less to type into your calculator. Does that make sense? Hopefully. Okay. Number 10. Force of gravity between two small masses, A and B, when placed very near each other is blah, blah, blah. What will the force between these objects be if both their masses are doubled and the distance between them is tripled? So one of these questions again. So we have Fg equals Gm1 m2 over r squared. And the value of this when they're placed at r, let's say, is 3.24 times 10 to the negative 7. So Gm1 m2 over r squared. Now, what are we going to do to that? We are going to take that, and instead of going Gm1, m2, we are doubling both their masses. So instead of having m, we're going to have 2m1 and 2m2. And then we're going to triple the distance between them. So we're going to go 3r squared, like that. And so if you figure this out, you get 2 times 2 on top. So you get 4g m1 m2. And then 3 squared is 9. So that's going to be 9r squared. And this, the value of this is 3.2 times 4 times 10 to the negative 7. So all we're going to do is take that 3.24 times 10 to the negative 7 and multiply it by 4 and divide it by 9. And you get 1.44 times 10 to the negative 7. Okay, so what you're doing here is you're stating what it originally is, and then you're seeing how it changes by doubling both masses and tripling the radius, and then relating that to the relationship of plugging that back in. Okay, 4/9. Good times. Any other questions before we start gravitational fields? Okay, let's start fields. So gravitational field, in physics, this idea of a field, it's not like a grass field or anything like that. It's we define it as an area of influence. Okay, so it's an area of influence. Now, the best way to imagine this is a campfire, or just a normal fire or whatever. If you've ever been by a campfire, hopefully you've been by a campfire. And if not, grab a candle and light it and see what happens. Okay, so you have this campfire. Okay, there's our campfire. There's our logs. Okay, the closer you get to it, the hotter it gets. And so if you imagine this campfire as being right here in the middle, there's an area of influence around that campfire where it provides heat. Okay, so let's say there's a certain distance where you can feel the heat, and over here it's cold. Okay, so if you're here, you feel the heat, but over here you don't. Okay, so there's an area of influence, and the closer you get, the hotter it gets. Okay, so as you approach the fire, the hotter it gets. Okay, so why the radius gets tripled? Oh, I need to go back to this. The radius is tripled because it says the distance between them is tripled. That's why. Okay, so the area of influence, the closer you are to the campfire, the stronger it gets. So that means that our area is dependent on how close you are to the object. Okay, now the other way you can affect the area is by building a bigger fire. Okay, if you build a bigger fire, that area is going to increase. It's now, you can now feel the heat further away, and the closer you are, the hot, it's going to be even hotter than it was before. Okay, so as you increase the size of the fire, the area of influence gets larger. Okay, now for the reason why I'm talking about a campfire is because gravity is an area of influence. Okay, so just like this field of heat, we have a gravitational field that surrounds any mass. Okay, and fields can be described as either vector or scalar. If you were talking about heat, you would talk about scalar. If you're talking about gravity, you would talk about a vector because it's directional. Okay, so heat measured in temperature, field is scalar. Gravitational fields are also force fields, and such are vectors. Okay, and we represent them by arrows. Now, if you think about the Earth, let's say, you know which way gravity goes. Okay, gravity goes this way. And so that's the direction of our vector arrows. They always point towards the mass. Okay. So that's why. Now, technically, the density of the arrows represents the magnitude of the field strength. So you would have a lot of arrows close to it. And then over here, it would be way less arrows because it's not as strong. Okay. So you have much more arrows surrounding the mass. Okay. So gravitational field strength. Now, this isn't something new. It's something we've already learned. And you're quite familiar with it. It's called acceleration due to gravity. Due to gravity. Okay, what we called G. Okay, that's what we're talking about. G, the value of G is the field strength. Okay, now remember that Fg equals mg, but because we have this new formula, hang on. I can't remember where this is supposed to be either. Acceleration due to gravity, gravitational field strength. Oh yeah, okay, so if Fg equals mg, then G will equal Fg over m. Okay, so it's whatever the force of gravity is divided by the mass that is accelerating. So this is the mass that is in the field. It's not the mass I'll just put a star here. Not the mass creating the field. Okay, that would be the mass of the planet. Okay, so the mass that's falling, like when we did Fg equals mg, it was the mass that was actually being affected by gravity. It wasn't the thing creating the gravity itself. Okay, now this formula works great on Earth. Okay, Fg equals mg is great. However, as soon as you lift away from the Earth, it changes. The value of G changes. Okay, remember our fire. The further away from the fire you get, the less heat you get. The further away from the Earth you are, the less acceleration due to gravity there is. Okay, the less pull there is. That's why I don't know if you guys watched the SpaceX launch recently. They had the shuttle speed on the screen the whole time, and you could see it increasing, and then all of a sudden it hits this point and it just starts skyrocketing. Like the speed starts changing way faster, and that's because they're escaping the Earth's gravity. Okay, there's two reasons. The value of G is getting less, which means that there's less pull towards the Earth, and there's way less air resistance. Okay, and so now you can go way faster because there's nothing slowing you down. Okay, it's really cool how you can see that like it's already a crazy acceleration, and then eventually gets to a point and it just starts changing rapidly, and it's really cool. Okay, so based off of this, remember that. So I'm gonna base it off of Fg equals mg. Okay, now remember that we have a new formula for Fg, and that is G m over r squared equals mg. Okay, now one of these masses is going to cancel out, and remember that this is the mass. I'll just point up here. It's the mass that's in the field. It's not the mass that's creating the field. That means that this mass right here is the mass creating the field. And so based off of this, we get a new formula that is G equals Gm over r squared. And this mass right here, m, is mass that is creating the field. Okay, in our case, it'll be a planet or a moon. Planet, moon, sun. Okay, those big objects in our university that actually, or in our universe, that actually have gravity. Okay, so let's look at the gravitational field strength on the surface of the moon. Now you can Google this. Okay, I think it's 1.62. I think. But let's find it using our our new formula. So G, gravitational field strength, acceleration due to gravity, is equal to G m over r squared. So this is going to be 6.67 times 10 to the negative 11 times the mass of the moon, 7.35 times 10 to the 22. How to define creating mass? How to know what? Exactly. How to know which mass is which? So I can define this as like, so let's think about this a little bit different. Okay, you have the Earth, you have the object. The object is affected by the force of gravity of the big object. Okay, this is the mass of the planet. Okay, we have defined this as the mass of the object times g. And so in our formula, we have Fg equals mg, so g, m of the object, actually I'm going to go m of the planet times m of the object over r squared equals m of the object times g. Okay, this is that formula rewritten with our new formula for Fg. And so we're canceling out MO. So what's left is MP, the mass of the planet. So you can define which masses are which based off of the formula there. I hope that answers your question. I just did something weird. I don't know what I did. Okay. So 6.67 times 10 to the negative 11, 7.35 times 10 to the 22, and then divide by the radius squared, 1.74 times 10 to the 6 squared. So 6.67 times 10 to the negative 11 times 2 divided by bracket 1.74 times 10 to the 6 squared equals, oh, that's right, G equals 1.62 meters per second squared. Okay, and the value is obviously, or the unit is obviously meters per second squared because it's acceleration due to gravity. Any other questions before we keep going? So if you look at this formula here, another way of expressing the units of G is newtons per kilogram. Okay, I know some of you are doing that already, but it's force of gravity over mass, so it's newtons over kilograms. Okay, so let's talk about the next example. A satellite orbits the Earth at a radius of 2.20 times 10 to the 7 meters. What is its orbital period? Okay, now in order to answer this, we have to come up with some sort of relationship of where the object is. Now keep in mind that there's the Earth, there's the satellite. Okay, the satellite's going to be going around like that because of the FG. Okay, now instead of dealing with FG, remember that anything that is traveling in a circular path has an AC as well. Okay, and that AC for a satellite, the acceleration, centripetal acceleration, is the exact same thing as G. So G is AC. For a satellite, the G, the acceleration due to gravity that's acting on it, causes centripetal acceleration, and that's how we're getting this. Okay, so now instead of doing all that other stuff, I can go G m over r squared equals, and then AC, we have a couple different formulas. We have v squared over r, but we want to know its orbital period, so that we have 4 pi squared r over t squared. Okay, so now we're solving for orbital period. So what I'm going to do is I'm going to cross multiply and then divide by gm. So I'm going to get r, not v. Okay, so I'm going to multiply both sides by r squared. Yes, g is equal to ac because fg is fc. Okay, so it's the same thing as doing this. fg equals fc. So gm1 m2 over r squared equals m 4 pi squared r over t squared, and all we're doing is canceling out an m. Okay, if you cancel out the m, then you get g equals ac. It's the exact same thing. Okay, so even if you set it up like this, that's totally fine. You're going to get the exact same answer. Okay, so we're going to multiply both sides by r squared. That's going to cancel out. We're going to multiply both sides by t squared. That's going to cancel out. And then I'm going to divide both sides by gm as well. So we get t squared equals 4 pi squared r cubed divided by gm. And then we're going to square root that. Square root, square root. Okay, so our formula becomes t equals 4 pi squared 2.20 times 10 to the 7 cubed divided by 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. Oh man, that's a lot of numbers. And we're going to square root that after. So 4 pi squared times 2.2 times 10 to the 7 cubed. Where's my cube button? There it is. Divided by 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. And then square root that, and we get t is equal to 32,464 seconds. Oh boy. Okay. Hopefully that makes sense. Does that make sense? The hard part about this is just keeping your numbers straight, and then like it's a lot of numbers to type into your calculator. So an important skill is calculator skills for this unit for sure, because it's, yeah, you can easily type in a wrong number. Okay, last thing for this topic, geosynchronous orbit. So geo means Earth and synchronous means same. So what that means is, so if we wanted a satellite to be at the same spot above Earth at all times, okay, so it, like, let's say we wanted to launch a satellite that hovers over Surrey all the time. Okay, so it just looks like another star in the night sky. It's not actually moving. We can do that. Okay, we can make it stay above one spot because we can match its orbital period with the period of the Earth, because the Earth rotates at a certain speed as well. Okay, so first of all, let's think about the following situations. So let's say we have identical satellites. Which one will be traveling faster? Satellite A orbits the Earth at twice the orbital radius of satellite B. Which one do you think travels faster? Anyone? Should we do some math for this? Okay, so if G is equal to AC, let's say we have the same satellite. The mass doesn't really matter, I guess. So we have GM over R squared equals V squared over R. Squared over R, that's what it is, right? So if you were to solve this for V, now keep in mind that, so we have R, but we also have another satellite that's going to R. So we'll set that up over here, GM over 2R squared, because it's double the orbital radius, right? equals v squared over 2r. So let's solve this one for v first. So we're going to multiply by r. Those are going to cancel out. And we get v equals the square root of gm over r. Okay, remember that formula we had? Now this one, we're going to multiply by 2r, but this is going to be 2r gm over 4r squared equals v squared. And so that's going to be 2r. And so the v here is going to equal the square root of gm over 2r. So which one's faster? This one's faster. Okay, we're dividing by, we have a 2 in the denominator, which means that the numerators, well, what do you call that, the outcome? I can't remember. The answer is going to be smaller. So the one that's closer is going to be traveling faster. Okay, so closer travels faster. Okay, and in this case, it's because G is stronger at that point. Okay, so we can apply the same thing here. Satellite A orbits the sun at the same orbital radius that satellite B orbits the Earth. Satellite A will go much faster. A is faster because, again, G is bigger or stronger, whatever you want to say. Okay, so the orbital period of the satellite depends only on the mass of the planet and the orbital radius of the satellite. It doesn't matter the mass of the satellite at all. So it stands to reason, therefore, that a certain orbital distance, the orbital period will match the rotation of the period of the planet. Okay. So let's find the orbital radius of a satellite that is geostationary above Earth's equator. In order to do that, we need the period of the Earth. Okay, how long how long does it take the Earth to do one complete cycle? Okay, and the answer is 24 hours. Okay, which doesn't help us because that's hours, so we need that in seconds. So we're going to multiply by 60 times 60, so 3,600. So the orbital period of the Earth is 86,400 seconds. Okay, so now we can apply the same thing here. G equals AC. Gm over r squared equals 4 pi squared r over t squared. And we need to solve for r. So it's going to be gmt squared divided by 4 pi squared equals r cubed. That's going to be a tricky one. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 86,400 squared divided by 4 pi squared. Uh-oh, I don't know how to cube root on this calculator. Yes, I do. Cube root that because it's r cubed. And you get, oh, I got it. R equals 4.23 times 10 to, I'm just going to round up. 1, 2, 3, 4, 5, 6, 7 times 10 to the, whoops, times 10 to the 7 meters. Okay, so that is the orbital radius. That's not the altitude. Okay, so it's, yeah, that's fine. We're good. We're good there. Okay, so it's, that's how you find that. So then we can find the orbital speed by applying that radius. Okay, so we can do that again. So gm over r squared equals v squared over r, and use that radius. So remember that v is equal to the square root of gm over r. So 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by our radius, 4.23 times 10 to the 7, and then square root that, and we get V equals 3,070 meters per second. Oh, that's fun. I think that's it. Time's at 10:15. Do we want to keep going? How long has it been? This is a pretty hefty lesson. The only issue I have is that you guys have that worksheet. That's fine. Okay, so let's stop right now. So I gave you that assignment to do. You can do a lot of it. Like the next part is to talk about the energy of satellites and all that stuff. So we'll do that on Monday. So I guess, how do I want to play this? So I guess let's do this. Let's do, so you can do 5.4 now, 5.4 worksheet. You can do the assignment, most of it. And then on Monday, we will do lesson 5. I think I called this lesson 5 today. Whatever, lesson 5. And then the assignment will be due Monday at midnight. Okay, so I'm making sure that you get most of it, or as much of it as you can, done now, so that on Monday you'll only have a few questions left. Only the energy questions. Do it at midnight, and then Tuesday we will do lesson 1 of electrostatics, and then the rest of the class will be like review. And then Wednesday morning, I will post the circular motion test. Okay, and then we'll probably do lesson 2 as well on electrostatics. And then Thursday will be lesson 3 or 4, or 3 and 4, or whatever, however far we get. And then I also have worksheets for electrostatics, so I'll have to fit those in there somewhere as well. But yeah, that's the plan for the next little bit. And it looks like this puts us all ready to Wednesday for lesson 2 on electrostatics. Let's say Thursday we do like lesson 3 and 4. And then Friday we might do lesson 5 and 6. I think there's 6 lessons. And then we might not get to very much of electrostatic or electromagnetism, because that's already pushing us to Friday, and that's going fairly quick. So we'll play it by ear. And I'm not too worried about finishing the course or not, but it'd be nice to, but I don't think it's a reality, because after this Friday we only have really only have 3 days left. So and one of those will be an electrostatics test. So yeah, well, we're not going to finish electromagnetism in 2 days, that's for sure. So that just means that each test becomes weighted more as well. But again, I'll take that into consideration when doing your final marks. Okay, I know that it's not quite fair to be doing this fast and not having the opportunity to redo things and all that stuff. So any questions?
Thank you.
No problem. Okay, so I will see you Monday, 8:30 should be good. Yeah, 8:30 should be good. And then, yeah, that's it. So have a great weekend.